Good day from ChemHelp ASAP. In this video, we will see an interesting application of SN2 and epoxide chemistry. The work in this video is reported in the Journal of Medicinal Chemistry and led by two scientists, Drs. Jesper Mathiesen and Daniel Pedersen at the University of Copenhagen in Denmark. The citation is on the following slides as well as in the video description. Here is our key reaction sequence. Before we start, I'll note that this odd group on the epoxide under the first reagent arrow. MNS, this group, has this structure. MNS stands for meta-nitrobenzenesulfonyl. If we put an OR group on it, then the entire MNSNO is an excellent leaving group, much like tosylate. So let's move on to the reaction. In the first step, we have a standard Williamson ether synthesis. We have a phenol in the presence of a base, potassium carbonate. If we deprotonate that hydrogen, we get a new phenoxide, and I'll just abbreviate the entire structure as R. So there's our phenoxide. Phenoxide is a nice nucleophile. It will attack the carbon bearing the leaving group and eject the leaving group, and that will give us our new ether, this new CO bond. So this SN2 reaction is on a carbon that is not a stereocenter, so we don't need to worry about stereochemical inversion. Furthermore, there is a stereocenter in the molecule, but that stereocenter is unaffected by this SN2 reaction. While this reaction looks simple, the reagent in step 2, this epoxide, has two electrophiles. One is the carbon that we attacked, the other is the epoxide. So researchers specifically selected the MNSO group so that the nucleophile would preferentially attack the left carbon instead of the right carbon, the terminal epoxide carbon. Selecting the right leaving group was important for controlling the regioselectivity of the nucleophilic attack. We finished by opening the epoxide with our amine. Again, we'll use an R group. This ultimately leads to our amino alcohol. I won't show all the steps, but here's the initial intermediate. We'll need to do 2 proton transfers to get to our final amino alcohol product. So let's now see why the scientists in Copenhagen made this molecule. On the screen, our product from the previous page is in the upper left. Below are 2 drugs shown as single enantiomers. Both are members of the beta blocker drug class. Beta blockers bind the beta-andrenergic receptor and are one of the most common drug classes for treating high blood pressure. Beta receptors have multiple subtypes, each with somewhat different biological effects. Some beta blocker drugs are not selective for one subtype over another. This non-selectivity can lead to unwanted side effects. The team at Copenhagen connected molecules like our previous product together into dimers. This big molecule in the middle of the slide is an example. You can see it contains 2 identical parts connected by a chain. By studying the binding of molecules like this larger dimer, researchers learn more about binding beta-adrenergic receptors, which may allow the design of safer and more effective beta blocker drugs. In conclusion, an SN2 and an epoxide opening began the synthesis of molecules that may help in the design of improved drugs. If you want to learn more about how the University of Copenhagen scientists prepared and studied these molecules, then check out the reference on this slide or in the video description. Please subscribe, like, or leave a comment. Take care.